Cool. Let's continue. I was at here. I solved the first part, and here I'm going to continue with the part 2. To remind the question, basically we were giving this grid, and these square tiles are our positions, and we are expected to find 2 tiles that create the biggest rectangle, and we like to have the area of this rectangle. We've done it. The answer was this. Now we are going on to the part 2. The elves just remembered they can only switch out tiles that are red or green. So your rectangle can only include red or green tiles. Okay? In your list, every red tile is connected to the red tile before, and after it by a straight line of green tiles. Wait, in your list, every red tile is connected to the red tile before and after it by a straight line of green tiles. All right. Okay. The list wraps, so the first red tile is also connected to the last red tile. Huh. Like this is connected. Like no, sorry. Like this one is also connected to this tile apparently. The list, I'm assuming it's input list. The tiles that are adjacent in your list will always be on either the same row or the same column. Using the same example as before, so tiles marked X would be green. Alright. In addition, all of the tiles inside this loop of red and green tiles are also green. So in this example, these are the green tiles. The remaining tiles are never red nor green. The rectangle you choose still must have red tiles in opposite corners, but any other tiles it includes must now be red or green. This significantly limits your options. For example, you could make a rectangle out of red and green tiles with an area of 15 between 11.1 and 7.3, and its size is 15, right? Or you could make a thin rectangle between these two. The largest rectangle you can make in this example using only red and green tiles has area 24. One way to do is between that and that. Using the 2 red tiles as opposite corners, what is the largest area of any rectangle you can make using only red and green tiles? Hmm. Okay. For example, so this is our. So what about this and this? Can we do something here? I think we can. And I think it's the answer. No, I think, but it's close, right? It's 3, 5 times 3, 15. But this is bigger. Okay, but this was doable. What about this thing? This and this. Uh, I think that's also doable, yeah. 7 times 13. Okay. Yeah, you could have this and this. You could have this and this as well. What about this and this? Not really. Because like just by looking at it into their combinations, like positions, can I assume that if like basically it should go this direction, go until the red tile is there. And for here, it needs to go this direction until the red tile is there. Um, so in order to select these ones, you need to check, is there something on this range uh, that blocks me, right? But I think that's not the case. So there can be red tile here, even red tile here, and red tile here. It's okay, like you can have red tile, but the problem here is the next red tile here appears this direction. Hmm. Hmm. I think there has to be some kind of relation that we can identify. Let's see. In your list, every red tile is connected to the red tile before and after it by a strain light of green tiles. Before and after. So like this is the before one, or like the list wraps. So the first red tile is also connected to the last red tile. Like let's have a look at the input. Yeah, basically 7 1, 11 1. So these are matching. Here this coordinates are matching. Here this one matching. Matching. Matching, matching. So there is a kind of linked list structure that you can utilize, but not really as well. Like, what was the positions that we chose this one and this one, right? So let's assume this is this one, this is, I don't know, 7-1, right? 7-1 probably. So this is 7-1. And the other one we would like to choose is this one, which is 11-7, yes. So this thing and this thing. Um, once you have these information, you naturally depend on the positions of the others. So you'd like to traverse the whole list somehow for each 2 points. Maybe you can do it once in the beginning, but okay, I'm ready to give up actually right now and come back tomorrow. Interesting. Alright, now I'll give up for now. I'll come back and do it tomorrow. Have a nice evening and see you tomorrow.